Hello friends, in this video I'd like to solve the following problem from the International Mathematical Olympiad 1990, problem number 4, proposed by Turkey. We wish to construct a function f from the set of positive rational numbers into itself, satisfying this equation. F of x f of y equals f of x over y for all positive rational numbers x and y. So it's a very interesting problem because we just need to construct one function. Just one is needed. Here are my hints. First, set x to be 1 to justify that our function is injective. Then set x and y to be 1 to find f of 1, which should allow you to see that f of y equals 1 over y, and our function is completely multiplicative. So f of xy equals f of x times f of y for all rational numbers x and y, positive rational numbers x and y. And in fact, this is not strictly necessary, but you may wish to observe that our functional equation is equivalent to these two conditions. So maybe it is easier to construct a function and to check that it satisfies these two conditions. And also notice that every positive rational number can be uniquely written as a product of primes to some powers, where these powers are integers. And this product, it looks like an infinite product, but in fact almost all exponents are 0. So in this product we have only a finitely many terms which are not 1. And also, to construct this function, enumerate the set of primes as p0, p1, p2, p3, and so on, and consider this function, which maps primes with positive even indices to reciprocities of primes with odd indices, and maps odd primes with odd indices to primes with even indices, and try to build your function from there. So give this problem a try, and I will see you in just a minute. Right, so let's start with setting. Let's take our equation and let's set x to be 1 in our condition asterisk. Well, then we have the following. F of y equals f of 1 over y, which means, notice that the function here is injective because f of 1 is non-zero. So the function, or maybe let's write that mapping which takes positive rational numbers, takes y and returns this, is injective. So f composed with itself is injective, which in turn means that the inner function must be injective. So f itself is injective. All right. Now let's set both x and y to be 1 in our equation asterisk. Then we have the following. Then f of 1 equals f of 1, and using the fact that our function is injective, we can cancel this outer occurrence of our function, which means that f of 1 equals 1 by injectivity. Which means that this equation, which I will mark double asterisk, it becomes double asterisk becomes the following. F of y equals 1 over y for all positive rational numbers. And I will mark this condition by a triangle. All right. And now I wish to do one more thing. Well, let's now replace, or maybe let's take our equation once again. It says that f of x, f of y, am I right? I am. F of x, f of y equals f of x over y. And now let's do the following. Let's replace y by f of y. Then we have the following: f of x, f of y equals f of x over f of y. But f of y, as we know it, f of y is just 1 over y. Which, right? How do I know it? By our condition triangle. By condition triangle. And also now let's replace x with x times y. Replace x by x plus x times y. And then we have the following. On the left hand side we have f of xy over y equals f of xy over f of y. Which means that, and I will write it in different color, f of xy equals f of x, f of y. And I will mark this condition square, and that holds for all positive rational numbers. Right. Very well. So if our function satisfies our condition asterisk, it must satisfy both triangle and square. And now I will prove the converse. Notice that if a function f satisfies both triangle and square, triangle and square, then we have the following. Well, f of x times f of y, well, I can write it as f of x, f of y, because of my condition square, because of square. And now f of y can be written as 1 over y in turn by condition triangle. So, which means, essentially, we have just proven that our condition asterisk is equivalent to the conjunction of condition triangle and condition square. So now I wish just to construct a function which satisfies these two conditions. So maybe let's write it. We want to construct a function f from the set of positive rational numbers into itself, satisfying both conditions triangle and condition triangle and square. How can we do it? Well, the basic idea is condition square talks about that our function is multiplicative. We know that every rational number can be written as a product of primes with positive or negative exponents. So in essence, it's sufficient to define our function over primes, because this condition that our function is multiplicative extends it uniquely to a function over all positive rational numbers. But also we need to satisfy this second condition, that f of f of y equals 1 over y for all positive rational numbers. And my idea to construct this function is the following. Let's enumerate the set of primes. So the set of primes, let's say that it's p0, p1, p2, p3, and so on. The order does not matter. It can be increasingly, so 2, 3, 5, 7, and so on, but the order doesn't matter. And I will consider first the following mapping. I will map primes with even indices. I will map them to the inverse of the next prime, and I will map primes with odd indices to primes, just to primes with even indices, preceding prime. So it maps to the preceding prime. And that allows me, and I will define my function, define f from the set of positive rational numbers into itself by the following formula. It takes some argument, and this argument can be written as primes raised to some exponents, and I define this function to be the following. Well, primes with even indices will go to their inverses. No, sorry. Let's write it in a better way. I will write the following. So primes of the type p0, p2, and so on will be mapped to pk plus 1 to the power minus alpha 2k, and primes with odd indices will be mapped to p2k just to the power 2 alpha k plus 1. Alright. And also, empty product is just 1, so 1 is mapped to 1. Alright. Now I will check that this function satisfies both conditions which are required. And also notice that this definition is correct because every prime can be written in just one way in this type of product. And also these products are really they converge because they almost all of their terms are number ones. So let's check that this function satisfies both conditions. So let's start with condition which I marked square. So let's write that x is a product pk to the power alpha k, and let's define y to be a product pk to the power beta k. And now I wish to first let's write f of xy. Well, f of xy can be combined in just one product, pk alpha k plus beta k. Alright, and now using the definition of our function, this product becomes the following. Even indices are mapped to primes with even indices are mapped to primes with next index, but with negative exponent. and primes with odd indices are mapped to the previous primes, and the exponent is wrong. Here should be minus alpha 2k minus beta 2k, just as in our definition. And here we have just alpha to the power 2k plus 1 plus beta to the power 2k plus 1. Now, I wish to write my products in different order. So first I will take this p2k plus 1 minus alpha to the power 2k. Then I will write product going from 0 to infinity p2k alpha 2k plus 1. Then I will write product p2k plus 1 minus beta 2k. And finally, I will write product p2k to the power space, so let's put it to the left. p2k to the power beta 2k plus 1. All right. And now let's take a look. These two products, they are it's just f of product over all indices pk alpha k. It's by the definition. And also the second two products can be written as product f of this argument. All right, and now we have just f of x times f of y. So indeed, our function satisfies the first condition, that condition which I marked square. And now we just need to verify the second condition. So let's compose. So condition which I marked triangle. Let's compose f with itself. F of y. So it's f of product over this product. And now, as we know it, it can be written in this form. Right, and now, using the condition square, which I have just demonstrated, we can change this into f of this times f of this second product. Yes, let's take a look. Yes, I have replaced exactly right. And now let's take a look. In the first product, we have only primes with odd indices, and these primes are mapped to even indices. To the same primes, the previous primes, the exponents stay the same. So we have p2k to the power minus beta 2k. And what about the second product? Well, the second product, we have only even indices. So these primes are mapped to the next prime, but we have a negative exponent. And now we can just combine these two products back into one product. pk to the power minus beta k. And this is exactly the same as pk to the power beta k, all to the power minus 1. And this is exactly y 1 over y. So indeed, our function satisfies also the second condition. So it satisfies both square and triangle. So our construction was in fact correct and it is finished. So this type of function works, which takes product, primes to some powers, primes with even indices are mapped to the next prime, exponent is the opposite, and primes with odd indices are mapped to primes with previous primes with even indices, the exponents stay the same. And that closes our problem. It's just a function satisfying our equation. There are probably more, but we were asked just to find one, so we have done exactly that. And that's it. A very nice problem. So thank you very much for watching. I hope that you've learned something new, and I will see you next time. Goodbye.